This is a video that's going to highlight some of the points that you might find important to think about in our Lecture 26 homework. Of course, remember we've got our regular written out homework advice. You can just use that. You don't need this, but I think it'd be neat if you look at this, even if you've already done the homework. It might be something that kind of makes more sense even. I wanted to talk about forces for the first 4 problems and then torques for the last 2. In the first instance, overall, I guess every problem practically, except where the acceleration is given, we need to calculate the acceleration. To do that, we look at the overall system. We've done this a long time. I've done this almost from the beginning of the semester. We know the masses, we know the net forces, we get acceleration. Now we use it and we put it in and look at any part where, you know, if we know the mass now, we know the acceleration, and we know some of the forces, we can find others. We can find internal forces. By the way, when a kid is pulling on a rope for those tug-of-war problems, she's kind of kicking forward against the ground, which means the ground is pushing back on her, and sure enough, then that force is in opposite to this tension, and opposite, of course, to the force on the ground. And that is our external force that we need to consider. The whole thing will be reversed if we were pushing. For torques, remember that when we're doing R cross F, you know, we've got some pivot, we've got some force at some distance R. We know the magnitude of the torque is Fr sine theta. Well, that R sine theta can be sometimes really conveniently, you know, remembered to be R perp, where R perp is the distance of closest approach when you run a line along the F, you know, past the pivot point. And sure enough, you know, R perp, if I take R sine theta, I get R perp. That's useful when you're looking at those door problems where, you know, the R perp is sometimes easy to read off. Finally, in the famous bridge to everywhere, you've got a situation where, let me think of a big brick, just to make this a little easier. Think of a big brick with, say it's very heavy, say some big mass M. It has, say, a center mass right in its center. And if I were trying to put this right on top of another brick that's going to be smaller, say, I would want to put that center mass, if I want it to be just on the verge of tipping over, so I can make it extend as far to the right as I can, I'm going to put that center mass just on the edge. Now what I want to know is, what's the new center of mass of the whole thing, because I'm going to put the whole thing just on the verge of tipping on another brick below it. You know it's along this line, you know it's going to be closer to this point than that, and you only need to know the x-coordinate of it. So I do a little center of mass calculation. It's convenient to call that guy's center mass 0 and positive x in this direction. So this guy's center mass is L over 2. And the overall center of mass now, x center mass will be m times L over 2 plus 0 divided by the total mass. It's really neat to consider m, in fact, to be n minus 1 bricks. And therefore, you know, the denominator is n, and we get ourselves just a 1 over n L over 2 calculation, and that's 1 over n. That's the heart of where you get the 1 plus 1/2 plus 1/3 plus 1/4 on the last page of the notes. And by the way, the harmonic series, if you took it to infinity, diverges, which is the heart of that problem. So you could stop here, but I'm going to just quickly go over the first 4 problems and make a couple of comments about them. First 4 problems, let's see, I'm trying to get this to focus here. First 4 problems. Number 1, I just have a force on one side, get the total acceleration, see how it's eaten up as I go to the right through, and you know, the internal forces get less and less and less. On the other hand, if I have a force on both sides, then, you know, just your F net equals ma stuff, your acceleration is 0, the F net's 0 all the way through, and therefore, in fact, all the internal forces are equal to capital F all the way through. And of course, you end up with, for example, anywhere, not F plus F, but F minus F in the net force on any piece because the acceleration is 0. In problem 2, we've got exactly the same thing with a rope instead of these blocks, where the tension will be constant all the way through for the same reason. Here, the only thing that's really going to be very different, is that with this, from just kind of a problem like that, is that this little m here will change the overall acceleration. And then once you have that acceleration, you go back and do the calculation exactly the same as before when you were looking for the tension in a rope. Here, if I have no mass at all, then if I pull on this, I don't feel anything. There's no resistance. Indeed, there'll be no force. I have no force that I can apply on this thing. And of course, you can prove it by saying F net is 0. And if I tried to put a capital F here, I'd get a contradiction, or I'd get a formula that just said F equals 0. Finally, here, on the other hand, I actually use F net equals 0 because the total acceleration is 0, whether it's m is 0 or not. And now I got F net, is 0, but it's consistent now with capital F not being 0. And overall, they cancel. And internally, then the tension just keeps canceling the F. The tension is F all the way through. Problem 3, I just wanted to point out that if two kids were pulling on each other and they were, on ice, they would just go towards each other. If one kid is standing on ground and the other's on ice, the system is going to go towards that kid. You're going to have an acceleration in this direction, and that's all because there's now an external force due to the ground, as I mentioned in a highlight. For the train, same story. I know the acceleration is given, therefore I know that this tension between the engine and the rest of the cars must be providing the MA of that. And if you were to look at the last car or any car, the tension in the coupling between here must be providing its mass times its acceleration, and these calculations are just like the previous. Finally, for the tug of war, you look at the whole thing like a system of, of a net external force equals the total mass times acceleration. You get an acceleration, and then you play the game again, piece by piece. In the case where you've got a zillion kids pulling against each other, the total acceleration is 0 because the net force is 0. And therefore, you can look at one side or the other and get an equation for the tension here, because you know that the tension here has to balance the force, the net force from all the kids pushing on the ground.